before we start, so I'm going to start again. Welcome everyone to this lecture 2 series on massive stars. First of all, I would like to remind you that the next lecture is going to take place in 2 weeks' time, so not next week, but in 2 weeks. And also, please mind that Europe is changing time to winter time zone, while other part of the world might not. So please check that you are on time and not 1 hour before or later. Yeah, so that's it. So for today we have Debasish Dutta working at ISTA with Ylva Goldberg, who is gonna talk about massive star structure. So Debasish did his bachelor studies at Hertzsprung University in India, and then he did his master's studies at Indian Institute of Technology, Palakkad. I hope I pronounced well. During his master thesis, he studied spur instability supernovae and the black hole mass gap, and he tried to see the various factors which can affect the maximum mass of black holes below the mass gap. So nowadays he's first-year PhD student at ISTA, as I said before, and the exact topic of his thesis is not yet fixed, which is kind of usual, but he is working on connecting binary models with stellar atmosphere models. And at present, he is trying to study how the spectra of the stars strip in binary evolves after the mass transfer. He does have a publication, so if you are interested, please look at the paper, which is published in ANA, which is Evolutionary Nature of puff-type strip star binaries and their occurrence in stellar populations. So I'm going to give you the floor, Debasish, if you are ready. And please let us know a bit more about massive star structure. And afterwards, we will open up for a discussion. And we really encourage everyone to participate to this discussion afterwards. So Debasish, if you are ready, then the floor is yours.
Yeah, am I audible?
Yes.
Hi. Yeah. So yeah, thanks for the introduction. Hi, I'm Debasish. I'm a PhD student at the Institute of Science and Technology, Austria. So today, I'll be speaking about the massive star structure in this second lecture of the lecture series, and mostly I'll be talking about the structure equations, although primarily I'll be focusing on massive stars, but then of course these equations are general and works in the other mass regimes also. Okay, so here's a brief outline of my talk. I'll begin with the introduction of what are stars and how can we study stars through the surface properties, and what are massive stars. Then I'd go into the formulation of the structure equations, which have mass conservation, the equation of motion, the energy conservation, the energy transport by radiation and convection. Together with it, I'll also be speaking about the equation of state, the equation for composition changes, and a bit on opacity. After this, I would talk about some important timescales which are relevant when discussing stellar structure and evolution, and I'll also be talking about some simple scaling relations which can be used, which is helpful to study some relations between some basic properties, and then I'll end with a summary of how the structure of a massive star can look like. Okay. So I'd like to begin with what are stars. So as we know, stars are objects which radiates energy from an internal source, and they're bound by their own gravity. And this radiation from internal energy, and the energy is generated in the interiors through nuclear reactions. And while studying stars, we make some assumptions, like we assume that a star is spherically symmetric. And also, when and to mention that when we are discussing spherical symmetry, we assume that there is no rotation. If there is rotation, then we no longer have spherical symmetry, and the and rotation will be discussed in one of the upcoming talks in this series. Next, we also assume that the star is isolated. That means it doesn't have it interact with any of the nearby companions. But stars can be in binaries or triples or higher orders, and also we can have star planar interaction. So we will have talks on this maybe in the next block of the lectures. And last, we assume that stars are formed with a homogeneous composition. Now here I have the HR diagram, which have luminosity on the y-axis and effective temperature on the x-axis. I've just made axis here, so for the labels. And to show that effective temperature, as we know, effective temperature increases as we go towards the left. In this HR diagram, this horizontal strip, we can see a diagonal strip in this HR diagram, which is known as the main sequence. So these are the stars which are converting hydrogen into helium. And these are by far the most abundant stars, and therefore we can see many main sequence stars in the HR diagram. So we also know the Stefan-Boltzmann law, and from this we can see that the radius of the star depends on the luminosity and temperature. For high luminosity and low temperatures, we have large values of the radius. And as we can see, as if we go for high luminosities and low effective temperatures, we can have the giants and the supergiants, which are named because they are larger in size than the main sequence stars. Now, these supergiants, they can be red supergiant or blue supergiant or yellow supergiant, depending on the temperatures. For example, in the Orion Nebula, we have the two of the brightest stars, the Betelgeuse and the Rigel. The Betelgeuse here is a red supergiant, and Rigel is a blue supergiant. And then we also have the white dwarfs, which are smaller in size, the main sequence, and these are the compact remnants of low mass star evolution. Now, now I'd like to speak about what are massive stars. Now, the definition of massive stars could be different for different people, but what are massive stars depends on what is the final fate of the stars. And very loosely, we can say that stars which undergo a core collapse can be called a massive star. So this happens when the initial mass of the star is greater than 8 solar mass or higher. Although this is not a very sacred quantity, and this can change depending on various properties. Here I have a plot between the initial mass of the stars and the evolutionary phase. Now what we see for the lower mass stars, evolve and end up as white dwarfs. It can be a carbon oxygen white dwarf, or for a little bit more massive stars, we can have oxygen neon white dwarf. And as we go to more massive stars, we can see that it goes through many burning cycles. It undergoes a core collapse and form neutron stars or black holes. And these are the massive stars. This is what the massive stars are. So we'll mostly be talking about the stars which undergo core collapse. So what is not mentioned in this diagram is what happens to stars when they are very high. So for very massive stars, there is a condition called the pair instability supernova, where the oxygen core collapse and there is a explosion with so high energy that there is no compact remnant. The whole star blows up. Okay, so now I have here some evolutionary tracks in HR diagram. So we computed with the Geneva evolution code. And as these numbers here represents the initial mass of the star, and as we go higher, we can see we have evolutionary tracks of increasing initial mass. And in the upper region here is where the evolutionary tracks of the massive stars have, and here are where massive stars reside. If we see in the HR diagram, and to mention that these evolutionary tracks are computed at solar metallicity and with no rotation. Yeah, so here we have some another HR diagram with some evolutionary tracks. Now, although the HR diagram is a good, beautiful tool, however, we have luminosity on the y-axis, and if we are to work with observations, what we get from the observation is a flux, and the flux depends on luminosity. We have a dependence on distance, and sometimes we may not have proper estimates of the distance. So at that time, what comes into handy is the Kiel diagram, which is a plot between the effective temperature and the surface log of the surface gravity. But however, as we can see in this Kiel diagram, as we go to more higher masses, the spacing between the tracks decreases, and we might not be able to say which track it belongs to. Therefore, both of these have some advantages and disadvantages of its own. Okay, from now I would like to go to the formulation of the structure equations of stars. I'd like to begin with the mass conservation. So assume a mass shell here. We have assume spherical symmetry, and with the mass dm, and we know the density is defined as the mass per unit of volume, where we can write the dm in this way, and we can have matter inflowing and outflowing out of this mass shell. So we can write the dm as a function of the position and the time, where this represents the mass that is contained, and here this represents the mass that's flowing in and out of the shell. I replace dr with vdt. Okay, now when we have no mass flux, when the mass flux is zero, then Tm is just this. And if we rearrange the term here, this is what is the first equation of stellar structure. And so with this, I come to the second formulation of the second equation, which is the equation of motion. So I look at the gas parcel in this spherical shell, and I see what forces acting on this gas parcel. So we have the forces due to gravity and the force due to the pressure. The force due to pressure can be from gas pressure or the radiation pressure. So we can write the equation of motion here, where we have m into the acceleration. Here we have the force due to gravity and the force due to pressure, and then which translates to this. Now, in most of its lifetime, a star remains in stable. It doesn't change much. So we can assume that the acceleration term is zero. And when the acceleration term is zero, we end up a situation like this. dp by dm is equal to minus gm by 4 pi r to the power 4. And this here is the second equation of stellar structure, which says that the star remains in a hydrostatic equilibrium for most of its lifetime, and which means that the force, which is the force due to gravity, which is pulling the star inwards, is being balanced by the force of the pressure, which is pushing the star outwards. Now I am to introduce a concept here when the star is in hydrostatic equilibrium, which is the pressure scale height. So I start with the second equation, that is the hydrostatic equilibrium, and using the first equation, I replace the dm in terms of dr, and so I get dp by dr minus g in times rho. So we assume ideal gas pressure and put this value of rho, put here, and just solve this equation. And what we get is P is P naught e to the power minus R by HP. HP here is the pressure scale height, which is defined by the modulus of dr by d of ln P, which is the distance. The pressure scale height is the distance over which the pressure decreases by a factor of E. It's very helpful when we're discussing the structure of the star, and it's useful when we'll be discussing convection. Okay. So till now we have two equations: the mass conservation, the hydrostatic equilibrium. So here we can see that these have mass as a function of the radius, the position, the pressure, and the density. So we need one more equation if we want to solve this. Here comes the equation of state, which is the relation between pressure and density. So the pressure depends on the density, the temperature, and the chemical composition. And the pressure could be in the form of a classical ideal gas, or when we go to and here which is rho by mu mu. So mu here is called the mean molecular weight, which is the average number of particles per unit atomic mass unit. So this actually this both of these quantities together represents the average mass. This mu, as we can see, it depends on the mass number. So for heavier element, we have heavier mean molecular weight. Okay, so we can have this ideal gas pressure, or we can also have the degenerate pressure when we're talking about ideal white dwarfs. So although not so much important for massive stars, but so this form of equations is called polytropes. And in addition to the gas pressure, we have the radiation pressure, which is due to the photons, which is given by 1 by 3 AT to the power 4. And the total pressure is a combination of the gas pressure and the radiation pressure, where these two terms make up for the gas pressure. This is for the classical ideal gas, and these are for degenerate quantities. Okay, now I move on to the energy generation in the stars. As I mentioned in the first slide, that energy is generated inside the stars through nuclear reactions, and and we know that for any two nuclear reaction to occur, we need the two particle crossing the potential barrier, and which requires energy, which is dependent on the density and temperatures. So these nuclear reactions are temperature dependent, and they starts by burning hydrogen to helium and goes on to carbon oxygen and in many burning cycles. So the first reaction that we have is the hydrogen fusing into helium, which occurs when temperature at a temperature of 10 to the power 7 Kelvin. And for the lower mass stars, this fusion happens through the proton-proton, the PP chain, where we have two hydrogen nuclei coming together and forming this helium nucleus. This is the by far this is the most dominant channel, but also this can have other branches where PP2, PP3, and this numbers in red represents the branching ratios. So for more massive stars, the dominant mode of hydrogen burning is not the PP chain, but as well as the carbon nitrogen oxygen cycle, where or the CNO cycle, where the carbon nitrogen oxygen acts as catalyst. So we do start with a carbon nuclei. We have a proton, so it's a hydrogen. So carbon acting with proton makes 13 oxygen. 13 nitrogen, and then we have a cycle, and at last we make nitrogen with a proton capture reaction makes this alpha particle or the helium nucleus. So so in this cycle we have three protons coming together and making up the uh, helium. And this CNO cycle is actually a bicycle where after this cycle we branch out from this 15 nitrogen to one more cycle, which is known as the ON cycle. So this is the CN cycle, and the second one is the ON cycle. So in this ON cycle, we have oxygen. We have the fusion of oxygen, therefore, which requires a higher Coulomb barrier. Therefore, this occurs at a higher temperature. So so usually, the CN cycle sets in first, and after some time, this ON cycle sets in. And this is because the branching ratio for the ON cycle is low, yeah, as I mentioned, because of the high Coulomb barrier. Now, in this cycle, the slowest reaction is the reaction where 14 nitrogen going to 15 oxygen. And since this reaction is very slow, it acts as a bottleneck and it congests the flow of nuclei. So it preserves so nitrogen 14 accumulates in the burning region, and therefore massive stars are predicted to have a large amount of nitrogen in their cores compared to the low mass stars. So as I said, the two reaction mechanisms, the PP chain, the CNO cycle. PP chain occurs in lower mass, and for more massive stars, we have the CNO cycle. Now, the switch from PP to CNO happens because of the temperature dependence in its energy generation rate. So this is the nuclear energy generation rate of the PP and CNO. For PP, it goes to the power 4, and for CNO, it goes as to the power 16. And so we have some proportionality terms here, which are dependent on densities and mass fractions. So the proportionality terms is generally higher for the PP chain. So therefore, when we have lower temperatures, we have PP chain, which is the most dominant form. But as we go to higher temperatures, this temperature term takes over, and we have CNO cycle. So this is a plot of the energy generation rate and temperature. As you see, at some point, we have PP chain in the beginning, and at some point it switches to CNO. Higher temperature means higher, more massive stars. So more massive stars, that's why I have CNO cycle as a dominant mode of hydrogen fusion. Now, although I was mentioning that CNO cycle happens for massive stars, but actually the transition from PP to CNO happens quite early, around 1.3 solar mass, which is not so massive. For more higher temperatures, we can have helium burning happening through the triple alpha reaction. And so where three alpha particles, so helium nuclei, combine to give carbon. And this generally happens at higher temperatures above 10 to the power 8 Kelvin. And when sufficient amount of carbon 12 has been created, we again have a reaction which forms oxygen. So in the helium burning, we form carbon. We form both carbon and oxygen. Now we can have after this we have the heavy elements burning. That is the we have the carbon burning, and I have mentioned the temperatures in the right hand side. The neon burning, the oxygen. Lastly, the silicon burning, which forms the iron core. Now, this is how the structure of a massive star looks. This is very simplified version, but this is how it looks like at the end stages. We have an iron core, and at the center, and we know the binding energy of iron is the highest, so further fusion is not possible. And once an iron core is formed, the core collapses as a result of no energy generation. So, yeah, so as we have seen, we have many reactions that are going inside the stars. So, if we want to write the equation for how this for the composition changes, so we can look. Let's say we have an element I, which is getting created in some nuclear reactions involving element K and L, and it's at the same time it's getting destroyed by reaction with some other element J. So, if you want to see how much of this element I is present, we look at the number density of this element, where Ni is given by the mass fraction times density divided by the total mass. And if we see how the mass fraction is changing with time, we can differentiate both and we can combine. I mean, we can just do this, and we have dxi by dt, some constant terms, times dni by dt, where dni by dt is how the rate of this reaction. Yeah, dni by dt can be given by the rate of the reaction. So we have dni by dt, how the number of this particular element I is changing, which is given by this RKL, which is the rate of this first reaction, the reaction in which energy is of this I is created. This is the term for creation, and minus the rates of this destruction term. Now, these reaction rates, these are generally computed or measured in the lab, and what goes in the modern statistical evolution codes are some tabulated forms of these reaction rates. Okay, so we have created energy. So obviously the energy is conserved somehow. So we consider a mass shell again with epsilon as the energy generation rate and L as a local luminosity of this specific shell, and we can write the the epsilon as dl by dm. Now this dl by dm, where we have epsilon, this epsilon can have various sources. For example, we can have the epsilon due to nuclear reaction, the energy generation due to nuclear reactions, where energy is getting created. We can also lose energy through neutrinos. Now, neutrinos have a long mean free paths, and they escape the star without reacting with any other particles, and therefore neutrinos carry energy as it escape the star. And neutrinos are important in the later part of the evolution. And then we can also have the epsilon, the energy change due to the gravitational expansion or contraction. I mentioned some time ago that the star remains in hydrostatic equilibrium for most of its lifetime, but at some point the star can contract or expand, and this is where this epsilon graph comes. Then also, then here we have the energy due to the energy changes due to the mass loss. Now this is important. It is not important for most of its for all the stars maybe, but the mass loss can be due to winds, which are important for massive stars. And this mass loss can also be when we are transferring mass from a star to when the stars are in a binary configuration, and there is a mass transfer. So this equation here is the third equation of stellar structure. So till now we have three equations: the mass conservation, the equation for hydrostatic equilibrium, and the conservation of energy. Next, we have energy. Since we have generated the energy, we need to transport the energy. So energy transport can occur through various ways. Can have diffusion, where energy is being transported by the motion of the particles, and in diffusion we can have radiation, where the energy is being carried by photons, or convection, where gas particles, the ions and electrons carry energy. We can also have convection, where the thermal energy is transported by the movement of the matter itself. And as I said, neutrinos take away energy with it because they have long mean free paths. Therefore, we have neutrino losses. So I would like to go over them. So first we have the radiation. Now, when we talk of radiation, we work in the diffusion approximation, where the mean free path of the photons is much less when you compare to the total length over which the transport is to be done. So if we want to go for a formulation for diffusion, we start with the diffusion equation. So let's assume we have some particles flowing, and this is given by the Fick's law, where J is the particle flux, grad of n is the density in the gradient of particles, sorry, a gradient in the density of particles, and D here is the diffusion coefficient. So similar to the particle diffusion, we can write the equation, we can analogous, we can write a equation analogous for energy. So where here we have the energy density, and here we have the gradient in energy density, and this D is the diffusion coefficient, which is given by 1/3 of the average velocity into the mean free path. And this average velocity for photons will be the speed of light. L here is the mean free path, which is given by 1 over the density, and kappa. Kappa here is the is known as opacity. So basically, we define the mean free path as 1 over rho into kappa, and this kappa determines the resistance of the stellar gas as it up to the passes of energy by radiation. And this opacity can be dependent on the temperature, the density, and the chemical composition. And this opacity can have various sources like the electron scattering, the free absorption, the bound free absorption, the bound absorption. And inside a star where most of the particles are ionized, the major source is the electron scattering. And similar to the chemical compositions, this opacities are for the stellar evolution codes. We use some form of tabulated opacities. Okay, so we were here. We have written the diffusion equation for energy. So now combining all this term into in here, we have the radiative flux is where D is 1/3 of the velocity, which is c, and the mean free path, and energy density. Now we know the energy density is given by a t to the power 4, where so if we put those values here, we have this flux in terms of the temperature gradient, and if this flux we can write as the luminosity by 4 pi r square, and if we rearrange, what we get is a temperature gradient. Okay, so long story short, we start with a diffusion equation, and when analogously we write it for energy, and we arrive at a temperature gradient. Now, using the first equation of stellar structure, we can write this dr in terms of dm. So what we have is dt by dm, have a gradient in terms of the mass coordinate. So if we want radiation inside the star, this condition must be fulfilled. So basically, this is temperature gradient required to transport energy by radiation, and these are only valid for large optical length. And as we approach the surface of the star, it becomes invalid, because as we approach the surface, we have large mean free paths. Therefore, this diffusion approximation no longer holds. Okay, so the next process is convection. So as I said, convection is when the energy is transported by the motion of the matter itself. Now, for example, let's imagine a pot of water boiling, and we put in some noodles there, and after some time it starts boiling, and as you can see, the random motion of particles, the particles moving here and there, and with that it carries energy along with it. So how does convection transport energy? For this, we need to go to 3D hydrodynamic simulation, and some of it is being which is done in here. And but we do have a simple 1D theory, which is known as the mixing length theory, and which goes like this. So let's say we have a gas parcel, and we have the proper condition for convection to set in, and after sometimes the gas parcel rises, and after traveling a certain distance, it mixes with the surroundings. And this distance over which it mixes, it's known as the mixing length, which is written in terms of the pressure scale height, which I mentioned some time ago. So this convection could be a very important mixing mechanism, and there will be more details in the next talk about convection, which is dedicated to convection. But in my talk, what I will mention is some basic formulation of convection. So we want to see when convection can take place. For that, let's imagine we have a bubble of gas here with and we have a stable situation. That means the temperature is determined by radiation now. So the density and pressure is similar to the surroundings, the environment. So we perturb this particle and this bubble and make it rise in a length delta r. And when it rises, in order to maintain the same pressure, it undergoes expansion, and the time scale for this displacement, upward displacement, is very less when compared to the time scale for heat exchange. Therefore, the bubble expands adiabatically, and when it reaches a certain distance, let's say delta r, we'll have new condition for the environment, we'll have new condition for the bubble. So the final density of the bubble can be written as the initial density rho1 plus the density gradient in adiabatic conditions, as I have said, times the length over which it is transported. The density of the environment is given by the initial density, which is rho1, plus the density gradient of the environment times the distance. Now, we can have two conditions here. If the density of the bubble is greater than the density of the surrounding, then the bubble will fall back. We have a stable situation here. Let's say we perturb the bubble, we make it go up, but then again it comes to the same position. We don't have any kind of convection here. But if the density of the bubble is less, then the bubble would go up. And this is an unstable condition, and this is where we have convection. So this here, when the density of the bubble is less than density of the surroundings, this is the condition for convection. This is this instability criterion. If we put in these values and we arrange it, this is what we'll get. The density gradient of in the adiabatic condition, the bubble is less than the density gradient of the environment. As I said, the environment is determined by radiation. So we write the density gradient of the environment as density gradient in radiation. Okay, so we have this instability criterion. Now, if we take the ideal gas and put in the values and do a little bit of calculation, what we will get is this form, where this term here is the radiative temperature gradient, and this term is the adiabatic temperature gradient. So the condition convection to occur is when the radiative temperature gradient is greater than the adiabatic temperature gradient, and this condition is known as the Schwarzschild criterion. Okay. So now we have the full equation for energy transport. Energy transport depends on the temperature gradient, which is equal to minus gmt by 4 pi r to the power 4 p times this grad, and this could be, and this can take the form of a adiabatic temperature gradient, or the radiative temperature gradient, or the adiabatic temperature gradient, depending on we have radiation or convection according to Schwarzschild criterion. And here I have the two plots. The first plot shows is for a 1 solar mass star. On the x-axis we have the radius. So here is the center of the star, and as we go right, we go towards the surface. And on the y-axis, what we have is this temperature gradients. So what you can see, for a 1 solar mass star, in the interior of a star, the adiabatic temperature gradient is larger. So we have radiation according to this condition. In the exterior, we have the radiative temperature gradient, which is higher. So in the exterior, we have convection. Now, if we see for a 4 solar mass star, which is larger, which is more massive, the the condition for convection and radiation is completely different. In the interior, we have this condition fulfilling, so we have convection, and in the exteriors, we have radiation. So low mass stars have radiative cores and convective envelopes, and massive stars have convective cores and radiative envelopes. And this is I'm saying about main sequence. This is valid in the main sequence. As the star further evolves, this changes, of course. So we finally have all the structure equations in one place. We have the mass conservation, the hydrostatic equilibrium, the energy conservation, and the energy transport equations. So these structure equations can be solved in a consistent manner, and for this we need three more quantities, which are the equation of state, the opacity, and the chemical composition equations, the changes due to chemical composition. And these are, as I said, these in the stellar evolution codes, we take this from some tabulated equation of states, opacity, or the rates. Now, if we see here in all these equations, the only equation that is depending on time is this changes due to chemical composition. So this is the condition that is responsible for the evolution of the stars. So the star evolves since the composition changes. When composition changes, the temperature changes, the density changes, the location of convection zones, and therefore we have therefore this is the term which is responsible for the evolution of the star. So this, as I said, this can be solved numerically, and today we have many cell evolution codes like the MESA, the STARS code from Cambridge, Kepler, the Geneva evolution code, and so on. And more about the evolution codes and numerical calculations will be dealt in the fifth talk of this series. Okay. So with this, I go to the next section, which is the time scales. So here I talk about the relevant time scales which are important in stellar evolution. So the first is a dynamical time scale. So this is a time scale that the star would take to grow or shrink if we disrupt the condition for hydrostatic equilibrium. So we have this equation of motion. Now, if however we remove this pressure term, let's say there is no gas, nothing, we just so there is no pressure inside the star, so this term no longer exists. So if we solve this, what we get, a dynamical time scale approximately something like this. And the example of this dynamical time scale would be core collapse, when at the end, let's say, where we have an iron core which is not producing energy, so the core just collapse in dynamical time scale. And this is very fast. For our sun, it's around 1600 seconds, which is half an hour. So if somehow we have to remove the pressure, I mean the energy happening inside the star, then the star would just collapse. So this is a catastrophic event. Next, we have the thermal time scale, and this is the time that the star requires to radiate the reservoir of its thermal energy if some of the nuclear reactions were cut off. This is also known as the Kelvin-Helmholtz time scale, which is given by internal energy by the luminosity, and which can be written as the potential energy by 2. This comes from the virial theorem, which not mentioned, but this is what it means: the potential energy and the internal energy. So the potential energy is given by gm square by r, and so an example of this thermal time scale would be the Hertzsprung gap. That is when, let's say, the star after the main sequence, the hydrogen is depleted, and the star now contracts. And when the star starts to contract, the star needs to find the star needs some time to react to the changes that is happening, and this happens in the thermal time scale. And this Hertzsprung gap is seen in this evolution tracks. This is the Hertzsprung gap, and then this thermal time scale is for our sun. It's around 1.5 times 10 to the power 7 years, which is much larger than the dynamical time scale. Next, we have the nuclear timescale. This is basically a timescale on which the star burns the nuclear fuel. So this is the due to nuclear reactions by the luminosity. So example, the burning on the main sequence. Now our sun, which is burning hydrogen to helium on the main sequence, this is burning the nuclear timescale. So the nuclear timescale for sun is around 10 by 11 years. So as we have seen, the dynamical timescale is very small, followed by the Kelvin Helmholtz and the nuclear timescale. Now, this is generally valid only in the beginning stages. Towards the end, the nuclear timescale actually becomes very short, and towards the end of the evolution, and it's shorter than the thermal timescale. That means the nuclear, the changes that nuclear fusion does to the interior no longer affect the surface properties. Therefore, in the evolution tracks, if we see the tracks doesn't change much at the end of the evolution. With this, I come to the scaling relations. Now, as we know, the one of the famous relation is the mass-luminosity relation, and this can be derived from simple scaling of the structure equations. So I take the equations 2 and 4 of the stellar structure, which is the hydrostatic equilibrium and the energy transport uh, equation. And then we do some simple scaling for this reaction equation. And then, so this is P by R, and here M by R square rho. Rho I can write in terms of mass and radius, put this here. And for ideal gas, the pressure depends on the rho and T. Again, we use rho here, and we can write something like this, where T now depends on mass by radius. From this equation, we can just do some simple scaling here and arrange the term here, and we can put this thing here, and we'll end up at L proportional to M cube. Now, this is something that we have seen most probably, and this is generally valid for. I mean, I've calculated this using simple scaling, but here also I have assumed gas pressure. But as we go to more higher masses, we have radiation pressure, which becomes more and more prominent. Therefore, the actual exponent for more massive stars look a bit different. So this is a plot between the luminosity and the mass. So we can see this this track here. It actually flattens after some time, and for massive stars around 50 solar mass, this takes the form of m to the power 3.5. And for very massive stars, which is dominated by only radiation pressure, this can even reach 1. So L is directly proportional to M. So we have the mass luminosity relation, and similarly, we can have the mass radius relation. Also, the relation between the luminosity and mean molecular weight. And again, these are for massive stars. This one. So where we can see the luminosity as a strong dependence on the mean molecular weight. So and this is and this can have some consequences, and which is this some evolutionary tracks. And if we see, this is where the star starts, where the main sequence starts, and this is where the main sequence ends. And as the star burns hydrogen to helium, we have higher mean molecular weight, and because of this high dependence, we have increasing luminosity here. So we have this mass luminosity relation, which goes as luminosity goes as m to the power 3.5. With this, we can estimate the lifetime of the stars. So the lifetime of the stars is given by the energy by luminosity, and which is around 1 by m to the power 2.5. So as we see, as we go to more higher masses, the lifetime becomes shorter and shorter. So for more massive stars, the massive stars live fast and die young. And I have a plot here which shows the lifetime of the stars with the initial mass. And there's a lot of things here, but what I wanted to show is the lifetime of this mass decreases as we go to more higher masses. So let's say for 2 solar mass here, the lifetime is around 10 to the power 3 mega year. For let's say 100 solar mass, we have 3 mega year. So with this, I come to how the structure of a massive star should look like. So the structure of a massive star, as I said we have convection in the interior and radiation in the exterior. So we have the convective zones here and the radiative zones here. Now, the convective boundaries can may not be very well defined. So the convection can extend a little bit, which is known as overshooting. This again, overshooting will be dealt very properly in the next lecture. And here I have a plot of the mass coordinate and the mass fraction. So this is mainly a proxy for radius as we go towards the surface. As we go for more higher mass coordinate, we go towards the surface. In the interior, we have convection. Outside, we have radiation. And it is just the beginning of the main sequence. So the hydrogen fusion is about to begin. So we have hydrogen, helium, and as we go further, we have seen hydrogen converting into helium and the convective boundary receding. And, and this is at the end of the main sequence. We can also see nitrogen here. And as I said, nitrogen is, we can find out that the massive stars are predicted to have nitrogen in their cores because of the slow reaction in the CNO cycle. In absolute terms, it's not much, but when compared to the low mass stars, we still have some nitrogen. And I just want to end with Kipton-Hahn diagram, which is a plot of the time and the mass coordinate. So as we go up in the y-axis, we go towards the surface, and as we go on the y-axis, x-axis, we have time here. So this is the beginning. We have hydrogen converting to helium. These green shaded regions are the convective zones. So the we also have mass loss in the stars. So therefore, the star is somewhat losing mass here. And as the star evolves, we have convections in the outer layers also. So this is the more evolved stage where we have these convection zones here and there, and this actually this purple colors here represents the energy loss due to neutrinos. So as I said, neutrinos are very important at the end stages of the evolution. So we have lots of neutrino losses here. And with this, I'd like to summarize what I said. I introduced some of the basic concepts regarding massive stars, then formulated the structure equations, the mass conservation, the hydrostatic equilibrium, energy generation, and energy transport. I also discussed the equation of state, nuclear reactions, and capacities. After that, I discussed some relevant time scales and some simple scaling relations. And at last, I showed summarize how the massive star structure can look like. Thank you.
Thank you, Debasish, for this fantastic talk. It was really interesting and a lot of equations. Thank you very much. Do we have someone willing to ask a question, make a comment, start the discussion? You can raise your hand and yes, Gloria.
Hey, good morning. Yeah, excellent overview. Thank you very much. The question I have is, are we going to get a talk in the near future on what happens when you have to include rotation?
Yes, it's in the it's after one talk. So next talk we have on convection, and the next talk is on rotation. After that.
Okay. Do we have another question or a comment? Yes, Sarah, please go ahead.
Yes, thank you. It was a very, very nice talk. My question is about the opacity, which is one of the ingredients of these models.
Yes.
And I know for the model atmosphere codes, this is super crucial and very hard to have the atomic data good for this. So how uncertain are these opacities that are needed for the stellar evolution? Yeah, and how do they affect the models?
I actually don't have much idea on the opacity tables or the atomic data. So
Okay.
if
If someone else has an answer to that, he or she is more than welcome. Maybe Ilva or Jo? No?
Sorry, I missed the question. Can you repeat it, Sarah?
Yes. So this opacity that goes into the models, I know for the stellar atmosphere models, this is very crucial and not always so certain. And I wonder how this plays a role in the evolution models and if there's large uncertainties or that kind of thing.
Good question. For sure, there is uncertainties in the opacities, and updated opacity tables are always useful and can change things. It looks like the models are not that horrible in terms of opacities at this point, but perhaps when you reach really high mass, I would guess, perhaps it would change more. I don't know. Jo, do you want to fill in?
Yeah, I can add to this. So currently we hope that we have, do you hear me, by the way? Sorry, do you hear me?
Yes.
Yeah. So currently we have the hope that the opacity tables are quite reasonable, but maybe one shall go a bit back into history, because I'm old, I can go back into history. So the opacity project, which was actually begun or has started, say, in the middle of the 1980s, was just initiated by some problems in stellar evolution, namely particularly by the problem of Cepheid variables, that they were not working as they should. And so at that time, the people also thought maybe there is a problem with the opacities, and indeed it was. And a large group of atomic physicists have sat together and then have developed all the required codes to set up these opacity tables, which are nowadays used. So this is more or less, I would guess, okay. With respect to the nuclear reactions, this is a slightly different story. So we had just discussed this with you and with Debasish in the preparation of the talk, that, for instance, a couple of these nuclear reactions are not so old. So certain of these reaction rates are not older than, say, 20 years or something like this. I hope that they are quite consistent, but they are still always in check, so they can be, or there are certain observational checks. So this is what I know. Maybe the specialists in the audience know more.
Thank you.
A specialist in the audience wants to comment on that? Or maybe later? I can see in the chat that we have a question, so I'm gonna ask it for the person who wrote it. So, lovely talk. In the structure equation section, you had an analytic expression for the radiation gradient, but not the convection one. How do we calculate that one?
Okay. So you mean this, right?
Yes.
Yeah.
Okay, so as I said, this comes from this dlnt by dp. So this is how we do this. Maybe I don't have a better answer. Maybe someone.
So it's very simple. I think you misunderstand the question. I mean, the question is only how to calculate the adiabatic gradient, and this is pure thermodynamics and basically depends on the so-called adiabatic exponent, and this adiabatic exponent depends on the composition, particularly on the number of free electrons compared to others, so whether certain elements are ionized or not. But this is simple thermodynamics and knowing the ionization equilibrium, which then is a certain needs to be calculated.
Okay, does that answer the question? Well, it's difficult, it's the chat. We're gonna assume it's answering the question. In the meantime, yes, thank you. Sergio, please go ahead.
Yeah, thank you very much, Debasish, for this very nice lecture. So if you can go to the basic equations, because I have one question for my own curiosity. And I know,
right?
Yes. So I know we are for the moment concentrated on single stars, and but I was curious to see, and maybe you don't know, but there is people in the audience doing also binary modeling. So when you have now mass added to the structure of your star, what are the equations that are modified, and it's only that you need to add a new term on mass accreted, or is also other quantities in all these equations that are changing to continue your evolution of the star?
If we add the mass in a binary, or if we lose the mass, so of course all other quantities will be affected by this, I guess. But I just wanted to show this, that in case we have mass loss, then we there will be a conservation of energy, and this is where it comes.
So it will be only affected this energy conservation, not, for example, the mass conservation, not necessarily, or at the very edge of the star, at the boundary, you have to take this into account also for the mass conservation, I guess, no?
Yeah. No, I think it will affect all the other equations as well.
Okay.
So maybe we ask our specialist, is Danny still here? No, he is not here.
Yes, he's here.
He is here. So what are you doing in practice when you plug some mass onto the star with these equations?
One thing to realize is that in a binary, the binary mass transfer happens somewhere, for most of the binaries happen after core hydrogen burning. Now, after hydrogen burning, most of the star is still in spherically symmetric equilibrium, and it's only the outer layers that are affected by the very strong mass loss. So actually, this can be summarized, and that can be modeled on a rather independent way for the final structure of your star. But I mean, so you need a good model in order to calculate the mass loss of the mass loser. But what about the mass gainer? This is another story.
Yeah, I guess this was a question by Sergio.
Yeah, so it's basically just to put mass and then continue your computation, or is that also there's a chain in the structure in some way, and then you have to take into account okay.
You drop the mass that is lost by the loser, you drop it on the gainer like some snowfall model. But I mean, this is certainly not true, because you can have the formation of a disk before you have accretion. So what is happening there is very, very, very uncertain.
Okay.
So what is happening when your period is, for example, a little bit smaller, so that you have a mass stream where the mass stream hits the gainer directly without forming a disk. What is happening there? So you know, if you have a talk on single stars and this talk lasts for 1 hour, you need at least 5 hours in order to explain what is happening during a rush loop overflow.
And then I guess also because since the composition is also taking, or is taking into account for the equation, also the composition is changing. So for the outer part is also taken into account for the modeling of the outer
Absolutely. It's not only the composition of the mass transfer, but you have a completely different diffusion in an accretor. And we are all aware that since a couple of years now, everybody is convinced that a lot of binaries, they merge. This is an exponent of accretion. Huh? So we are not yet there.
Okay, so probably we'll learn more. If there's a block on binary evolution, we will learn more on all this.
Yeah, you need a block. And in the
Yeah, we
past,
will have a block, Danny, and I hope you will act as a supervisor. This will be exactly in 1 year.
Okay,
Okay.
thank you.
Okay. Yes, Elek, please.
Hi, and thank you very much for the great presentation. I had a question concerning your slide 58, short question. When you show Ilva's plot of the profile of chemical composition and the convective and radiative zones, yeah, this one. So the fact that the convective zone recedes as you enrich the material in helium and deplete it in hydrogen, is it due to the Ledoux criterion? So the fact that your convective and stability is not just the Schwarzschild criterion, but you also have to take into account the chemistry?
Yes, I guess so. I have not mentioned the Ledoux criterion here, but yeah,
And so the higher the mean molecular weight, the less convective and stable you are?
yes.
Mm-hmm. Okay, cool, thanks.
You're muted, Sophie.
Thank you. Do we have other question? And especially here, I would like to invite the PhD student and young postdoc to ask the question, because this is your opportunity to ask all the question you want. This is made mainly for you to come up with the question you want to ask. So please, yes, Thomas. You can ask a question.
Yeah. Hello. Yes. Nice talk. I just wanted to come back on the slide 45, please. Yeah. On the equations, you said that the gradient, the nabla gradient, is equal to nabla add. In case of convection, but if I'm not mistaken, that's an approximation. And
Yeah.
Yes.
yeah. Because in some cases you have a very higher differences between the real gradient that you should use in the equation and the adiabatic gradient in the envelope of massive stars.
Yes. So actually, I just mentioned a very simple term here for the Schwarzschild criterion. So there can be other, like I have not mentioned the Ledoux criterion, which also involves the mean molecular weight, and therefore, obviously, this is a very simplification of this whole process.
No. So just let me comment on this. Basically, you have a couple of limiting cases and the reality, as you have just said, namely also the envelope will not, or the outer parts, the ambient medium, sorry, the ambient medium will not be completely in radiative, will not show a completely radiative gradient. The bubble will not be completely adiabatic and so on, but at least the radiative and the adiabatic one are limiting cases. The most important point in this game is something which Debasish has not mentioned, just because we will talk about this next time, namely, of course, that the bubble per se is not always adiabatic, namely when you have additional processes, and one important process, for instance, is radiation, which can leave the bubble and cools it, and then the bubble will be no longer adiabatic, and only when the cooling, when this kind of radiation cooling is more or less negligible, then we really have more or less an adiabatic case. Otherwise, it's somewhat with a different slope. But as I have convinced myself in a couple of all these codes, not in all, but in a couple of these codes which are mentioned here, indeed, they are then either using the radiative or the adiabatic one, and they don't make really big differences, that there are also possibilities in between. So, but this can be done.
Okay, thank you.
Okay, do we have other common questions? If you are too shy to ask, you can still send me a message and I can ask the question for you.
No.
No, I don't see anything.
Then we are done.
I guess so. It's your last chance. 3, 2, 1. Then I suggest we wrap up here and we thank again the speaker, Debasish, and we thank again also the supervisor, Ilva and Joe. And we meet up in 2 weeks' time. And please check out your time zone, as I said at the beginning, because Europe is changing time. So thank you very much for today and see you in 2 weeks.
Debasish, please stay here.